Let us begin with something deceptively simple. When we say dimension, most people imagine directions: left-right, forward-backward, up-down. But in physics, a dimension is something deeper. A dimension is a way reality is allowed to change. If a universe has a dimension, something in that universe can vary independently along it. This definition sounds abstract, but it controls everything that can possibly exist. Imagine a universe with 0 spatial dimensions. There is no space, only a single location. Nothing can move. Nothing can have size or shape. Objects cannot be next to each other. Even if time exists, change has nowhere to go. Now imagine 1 spatial dimension, a line. Objects can move forward and backward, but that is all. They cannot pass each other. They cannot go around obstacles. If 2 objects collide, there is no sidestep. Interaction becomes inevitable. Already the rules of existence are different. Now imagine 2 dimensions, a flat plane. Movement becomes richer. Paths can curve. Avoidance becomes possible. But rotation behaves strangely. Knots cannot exist. Complex machinery is impossible. Now imagine 3 dimensions. Volume appears. Knots exist. Vortices form. Fields can wrap, twist, and stabilize. Only now does complex structure truly emerge. This is not coincidence. Here is a statement that sounds philosophical but is mathematically precise. The number of dimensions determines which physical laws are possible. Not the constants, not the parameters, the very form of the laws. For example, stable planetary orbits exist only in certain dimensions. Long-range forces behave differently in different dimensions. Waves disperse differently. Information spreads differently. Even causality behaves differently. So when we ask, what if the universe had one more dimension, we are not asking about decoration. We are asking whether atoms, stars, or observers could exist at all. We almost never question why space has 3 dimensions. Why? Because our brains evolved in 3 dimensions. Our senses assume it. Our language encodes it. Our intuition is trapped inside it. 3 dimensions feel inevitable, almost sacred. But physics has never treated them that way. From the perspective of mathematics, 3 is not special. From the perspective of physics, however, it might be dangerously precise. And this raises a profound possibility. Perhaps 3 dimensions are not arbitrary. Perhaps they are selected by stability. To explore this, we must move from intuition to theory. Before we speculate, we must respect a rule. If physics already speaks on a topic, we must listen first. Extra dimensions are not a fringe idea. They are embedded deeply in theoretical physics. Einstein changed our understanding forever. In relativity, space and time are not separate. They form a single entity, space-time. This space-time has 4 dimensions, 3 spatial, 1 temporal. Time behaves differently. It has a different sign in the metric. It enforces causality. It cannot be freely traversed. Yet mathematically, it is inseparable from space. This teaches us something crucial. Reality does not care about human intuition. If time can be a dimension, strange, directional, asymmetric, then additional spatial dimensions are not radical at all. In 1919, Theodore Kaluza extended Einstein's equations by 1 dimension. He did not add new forces. He did not add new assumptions. He simply asked, what if space-time had 5 dimensions? When the equations were rewritten, something extraordinary happened. They split naturally into Einstein's equations of gravity and Maxwell's equations of electromagnetism. Electromagnetism appeared as geometry. Later, Oscar Klein suggested the extra dimension might be compact, extremely small, rolled up like a circle. This was not imagination. This was mathematics demanding interpretation. 1 extra dimension unified 2 fundamental forces. Reference: Kaluza, 1921, Klein, 1926. Over the last century, string theory requires 10 dimensions. M-theory suggests 11. Brand world models place our universe on a 3D brane. In all cases, extra dimensions appear not because physicists want them, but because without them, the equations break. This is critical. Extra dimensions are often required for mathematical consistency. But we are not asking about 10 dimensions. We are asking something subtler and more dangerous.
Many extra dimensions push physics far from familiarity. But one extra spatial dimension keeps reality almost recognizable. Almost. This is where balance becomes fragile. Small changes in dimension alter force laws, destabilize structures, break hidden symmetries. One extra dimension is not dramatic, it is surgical, and that makes it the most revealing case. Now we reach the core physical issue. Forces do not choose their distance laws. Geometry forces them. In 3 dimensions, gravity behaves as F is proportional to 1 over r squared. Why? Because influence spreads uniformly in space. As distance increases, the influence spreads over a spherical surface. Surface area grows as 4 pi r squared, so intensity drops as 1 over r squared. This is geometry, not preference. In 4 spatial dimensions, the surface of a hypersphere grows as r cubed, so forces behave as F is proportional to 1 over r cubed. This tiny mathematical change has enormous consequences. In 3 dimensions, planets orbit stars, electrons bind to nuclei, structures persist. In 4 spatial dimensions, orbits are unstable, small disturbances grow, systems either collapse or escape. This is not speculation. It follows from classical mechanics and is formalized in Bertrand's theorem. Only 2 force laws produce stable closed orbits, inverse square and harmonic oscillator, and inverse square works only in 3 dimensions. Without stable orbits, no atoms, no chemistry, no planets, no life. At first glance, the universe seems impossible. This conclusion assumes infinite extra dimension, no compactification, no field confinement. Modern physics allows compact dimensions, warped geometries, fields trapped on lower dimensional surfaces. So the universe might survive 1 extra dimension, but only under very special conditions. And this raises the deepest question so far. Is 3-dimensional space necessary or merely selected because it is stable? So far it seems that 1 extra spatial dimension destroys the universe. No stable atoms, no planets, no chemistry. But physics rarely ends with the simplest case. The arguments we made assumed something very specific, that the extra dimension is large, that it extends infinitely like the others, that all forces can freely spread into it. What if that assumption is wrong? An extra dimension does not need to be large. It can be curled up, compact, closed on itself. Imagine a garden hose. From far away, it looks like a 1-dimensional line. Up close, you see a second circular dimension wrapped around it. An ant walking on the hose experiences forward-backward motion, large dimension. Around the hose motion, small dimension. But a human observer far away sees only 1 dimension. This is not an analogy invented for popular science. This is exactly how compact dimensions work in physics. Klein's idea was simple and powerful. What if the 5th dimension is circular, extremely small, near the Planck scale? Then, motion along it appears quantized. Momentum in the extra dimension appears as electric charge. The dimension becomes invisible at low energies. This explains why we don't observe extra directions. Physics looks 3-dimensional at human scales. Mathematically, compactification changes everything. The extra dimension exists, but its effects are subtle and indirect. This is the crucial question. If the extra dimension is compact, field forces may not spread freely. Inverse square laws may re-emerge at large scales. Atomic and planetary stability might survive.
And indeed, calculations show, at distances much larger than the compactification radius, forces behave almost normally. Deviations appear only at very small scales. So, a universe with one extra compact dimension could look almost exactly like ours. But almost is doing a lot of work here. Even if the dimension is compact, fields can still vibrate into it, energy can leak, new modes appear. These are called Kaluza-Klein modes. Each particle gains a tower of heavier states, extra mass from motion in the hidden dimension. If these effects were large, atoms would destabilize, nuclear reactions would change, stars would burn differently. The fact that we do not observe these effects tells us something profound. If extra dimensions exist, they must be extremely small or extremely well hidden.
So far, we have reasoned mostly classically, but reality is quantum, and quantum mechanics is far more sensitive to dimensionality than classical physics. The Schrödinger equation contains a Laplacian operator, boundary conditions, normalization constraints. All of these depend on the number of dimensions. Change the dimension and energy levels shift, wave functions spread differently, bound states may disappear entirely. This is not cosmetic. Quantum stability itself is at stake. Physicists have studied hydrogen-like atoms in different dimensions. The results are unsettling. In 3 dimensions, bound states exist, energy levels are discrete, atoms are stable. In 4 spatial dimensions, the Coulomb potential weakens faster, wave functions spread, bound states become fragile or vanish. In many cases, no stable ground state exists at all. No ground state means no atoms, no chemistry, no matter as we know it. In higher dimensions, position uncertainty increases, momentum space grows, confinement becomes harder. This means particles resist localization more strongly. Structures blur, sharp boundaries dissolve. The universe becomes less crisp. The more dimensions space has, the harder it is to trap anything. This is a deeply counterintuitive result, and a deadly one for complexity. Quantum field theory also changes. In higher dimensions, many theories become non-renormalizable. Vacuum fluctuations grow. Energy densities diverge faster. In simple terms, empty space becomes more violent. Stability becomes harder to maintain. Once again, dimensionality appears tuned for calmness. Now we move into deeper territory. If dimensions affect forces, quantum mechanics, stability, they must also affect entropy, information, the arrow of time. Entropy counts the number of accessible microstates. Microstates live in phase space. Phase space dimension increases with number of spatial dimensions, degrees of freedom. More dimensions mean explosive growth of possible states, faster entropy increase, harder maintenance of order. In a higher dimensional universe, systems thermalize faster, structure decays sooner, memory fades quickly, order becomes fragile. Stable information requires isolated states, energy barriers, long-lived structures. Higher dimensions increase decay channels, increase noise, increase coupling possibilities. This is why black hole entropy scales with area, not volume. It is not accidental. Dimensionality constrains how information survives. An observer is not just a brain. An observer is a stable physical system, capable of memory, resistant to noise, able to form long causal chains. Higher dimensions work against all of these. This suggests a chilling possibility. Perhaps universes with too many dimensions are not empty, they are unobservable from within. Across classical mechanics, quantum mechanics, thermodynamics, information theory, we see the same pattern. 3 spatial dimensions sit at a narrow point of stability. One more dimension does not gently modify reality, it pushes it toward chaos. Whether dimensions can change dynamically. Up to now, we have treated gravity mostly as a force, But in modern physics, gravity is geometry. So if dimensions change, geometry itself changes, and with it the meaning of motion, causality, and even existence. General relativity tells us something radical. Matter does not move through space, it moves along space-time geometry. Space-time curvature determines orbits, free fall, light paths, horizons. This curvature depends explicitly on the dimensionality of spacetime, the Einstein field equations. Change the number of dimensions and gravity becomes a different theory. In d-dimensional spacetime, Einstein's equations generalize naturally, but their consequences do not. In higher dimensions, curvature spreads differently. Gravitational fields weaken faster. Black hole solutions change form. For example, Schwarzschild black holes exist in any dimension, but their stability changes dramatically. In 5 spacetime dimensions, 4 space plus 1 time, black holes can become unstable. New objects appear, black strings and black brains. These objects do not exist in 4D spacetime. They can stretch, fragment, or collapse unpredictably. This is known as the Gregory-Laflamme instability. Reference: Gregory and Laflamme, 1993. Already, gravity looks less well-behaved. In our universe, stars live for billions of years. Orbits persist. Structures self-regulate. In higher dimensions, gravity's long-range coherence weakens. Self-organization becomes harder. Collapse and dispersion compete violently. This suggests something profound. Gravity becomes less hospitable to structure as dimensions increase. Not stronger, not weaker, less organized. Causality itself depends on dimensionality. Light cones behave differently in higher dimensions. The spread of null rays changes. Horizons form differently. Information trapping becomes unstable. This affects black hole evaporation, cosmic censorship, predictability of spacetime. A universe with one more dimension may still have causality, but it becomes fragile, less forgiving of perturbations. Now we step back and ask a larger question. Could a universe with one extra dimension even form in a stable way? To answer this, we must look at cosmology. The Friedmann equations governing cosmic expansion depend on energy density, pressure, curvature, dimensionality. In higher dimensions, expansion rates change. Dilution of matter accelerates. Structure formation is suppressed. Galaxies require slow expansion, gravitational clumping, long cooling times. Extra dimensions work against all three.
Inflation is already delicate. It requires fine-tuned potentials, controlled quantum fluctuations, graceful exit mechanisms. In higher dimensions, field dynamics change, vacuum decay channels multiply, instabilities grow faster. This makes sustained inflation harder to achieve. A universe may inflate, but fail to reheat properly. Some theories propose the universe began with many dimensions, most dimensions dynamically compactified, only 3 expanded. This is not philosophy, it is studied physics. Mechanisms include string gas cosmology, dynamical moduli stabilization, brain dynamics. In these models, 3 dimensions expand because only 3 are stable. The rest collapse or freeze. Reference: Brandenburger and Vafa, 1989. This is a stunning idea. Dimensionality may be selected by cosmic evolution. A universe with one extra dimension might begin, expand, cool, but fail at forming long-lived structure, producing observers, preserving information. It is not dead, it is almost alive, and that may be the most unsettling outcome. So far, extra dimensions appear hostile, but modern physics offers a clever workaround. What if we live in 3 dimensions, not because others don't exist, but because physics is confined? In brain world models, space has higher dimensions. Matter fields are confined to a 3D surface, a brain. Gravity leaks into the bulk. This explains why forces look three-dimensional, why gravity is weak, and why extra dimensions remain hidden. Our universe becomes a surface in a higher dimensional space. Field localization requires special potentials, stable configurations, fine-tuned geometry. If localization fails, matter leaks, constants drift, physics dissolves. A universe with one extra dimension may survive, but only with extra structure added. And this raises a disturbing point. Three-dimensional space requires no confinement, requires no localization, requires no hidden mechanisms. It is self-supporting. A universe with one extra dimension must actively suppress it, hide it, neutralize its effects. This suggests a hierarchy. Three dimensions are not just possible, they are natural. Extra dimensions are possible, but costly. Across gravity, quantum theory, cosmology, field localization, we see the same theme. Complexity survives only when dimensionality is restrained. One more dimension does not destroy reality outright. It pushes it toward dependence on fine-tuning, confinement, and special conditions. So far we have treated dimensions as fixed, but physics does not actually demand this. In fact, some of the most advanced theories suggest something far stranger. Dimensionality itself may be dynamical. In higher dimensional theories, the size and shape of dimensions are described by fields. These fields are called moduli, radians, geometric degrees of freedom. They can oscillate, evolve, destabilize. This means dimensions are not static backgrounds, they are participants in physics. If dimensions can evolve, then an extra dimension could slowly grow, or slowly shrink, or fluctuate quantum mechanically. This would cause physical constants to drift, force laws to change, atomic spectra to shift. We do not observe this, so if extra dimensions exist, they must be extremely rigid, deeply stabilized, frozen very early in cosmic history. This adds another layer of fine balance. Stabilizing dimensions requires special potentials, extra fields, non-trivial topology, energy costs. In other words, a universe with extra dimensions must work harder to stay the same. Three-dimensional space does not. It is dynamically quiet. Some theories suggest the early universe passed through phases with different dimensionality. Dimensions froze out like phases of matter. In this picture, reality once had more freedom. Then symmetry broke, leaving only three extended dimensions. This resembles crystal formation, symmetry breaking in particle physics, phase transitions in condensed matter. Dimensionality may be emergent, not fundamental. Now we ask a different kind of question. Not can matter exist, but can thinking systems exist? Modern physics increasingly views reality as information flow, state transitions, computation constrained by physical law. An observer is a physical computer embedded in the universe, limited by noise, entropy, and decoherence. Dimensionality controls all of these. In higher dimensions, more interaction channels exist. Noise pathways multiply. Decoherence accelerates. This means memories decay faster, computations fail more often, long causal chains break. Reliable computation becomes harder. Memory requires energy barriers, metastable states, protection from fluctuations. Higher dimensions lower these barriers, increase fluctuation access, destabilize stored information. A universe may be physically rich, but cognitively barren. This suggests something unsettling. Extra dimensions may allow matter, but suppress meaning.
In three dimensions, structures can be isolated, noise can be screened, error correction can exist naturally. This is not philosophy, it is thermodynamics and information theory. Three dimensions sit at a balance point. Enough connectivity for complexity, enough isolation for stability. One more dimension tips the scale. Quantities like electron mass, fine structure constant, gravitational strength may be geometric effects, projections of higher dimensional structure, ratios of compactification scales, and extra-dimensional theories. In extra-dimensional theories, changing geometry changes constants. Constants become environmental, not absolute. This reframes a famous mystery. Instead of asking, why do constants have these values? We ask, why does geometry settle into this configuration? In a universe with one extra dimension, constants become fragile. Small geometric shifts cause large physical changes. Three-dimensional space locks constants in place, protects regularity. Once again, simplicity equals robustness. Across everything we've examined, forces, quantum mechanics, gravity, cosmology, information, constants, we see a pattern that is not anthropic hand-waving. It is structural selection. Only certain dimensional configurations are dynamically stable. Observers are not special. They are consequences. At this point, the answer is no longer simple. A universe with one extra dimension can exist, can form matter, can briefly organize, but it requires stabilization, requires confinement, requires suppression, requires protection mechanisms. Our universe does not. That difference matters. At this stage, many discussions reach for a familiar explanation. If the universe had more dimensions, we wouldn't be here to observe it. This is the anthropic principle. But relying on it too quickly hides something more interesting. The anthropic principle says only universes compatible with observers are observed. This is logically true, but physically empty. It does not explain why those universes are stable, why others fail, why certain structures persist. It replaces mechanism with inevitability. Physics seeks reasons, not excuses. What we have seen repeatedly is not observer selection, it is stability selection. Across disciplines, orbits, atoms, fields, information, geometry, certain configurations persist, others decay. Three-dimensional space allow long-lived complexity, resist perturbation, self-correct. A universe with one extra dimension is not forbidden, it is unstable by default. This is a much stronger statement. Not anthropic, not metaphysical. Something closer to only dynamically stable worlds endure long enough to be noticed. Observers are a byproduct, not a cause. Is three-dimensional space an attractor state? Now we ask a question few discussions dare to ask. Could three-dimensional space be a natural endpoint of cosmic evolution? In many systems, fluids, climate, chemical reactions, quantum fields, certain states act as attractors. Regardless of initial conditions, systems evolve toward them. Perturbations decay, stability emerges. What if dimensionality behaves the same way? In early universe models, higher dimensions may exist. Expansion destabilizes them. Only some dimensions continue growing. Three dimensions may minimize energy, maximize stability, suppress chaos. The rest collapse, compactify, freeze. This is not philosophy, it is studied mathematically. Three dimensions may not be chosen, they may be what remains. A universe with one extra dimension has more degrees of freedom, more instability channels, more decay paths. Even if it forms, it leaks, it fragments, it localizes itself back toward three. This reframes the question. We are not asking, why does space have three dimensions? We are asking, why does space stop losing dimensions at three? Now we reach a quiet, disturbing thought. What if the universe does have one more dimension, but it cannot grow, cannot influence,
cannot organize? What if it exists but is silenced? An extra dimension may be present in equations, affect constants subtly, shape geometry indirectly, but never support motion, store information, host observers. It becomes a mathematical necessity, a physical constraint, a silent background. Not absent, just inaccessible. In this view, we do not live in all dimensions. We live in the stable projection of them. Reality is not lower dimensional. It is filtered. What we experience is what survives. At this depth, the original question has transformed. It is no longer, what if the universe had one more dimension? It has become, what does reality remove in order to remain coherent? And this question does not want an answer. It wants reflection.
Now we must talk about something quieter, but just as decisive. Topology. Topology is not about distance or force. It is about what can exist at all, regardless of scale. In 3 spatial dimensions, knots exist, links exist, braids exist. This seems like a curiosity until you realize knots are topological memory. They preserve structure, resist deformation, encode history. DNA supercoiling, magnetic flux tubes, vortex rings, protein folding, all rely on topological stability. In 4 spatial dimensions, all knots can be untied. No matter how tangled a loop is, it can be smoothly deformed into a simple circle. This is a mathematical theorem. Topological protection disappears. Many stable structures lose their robustness. Memory encoded in structure dissolves. Higher dimensions are too permissive. They allow escape routes that destroy persistence. Complex systems rely on constraints, bottlenecks, inescapable configurations. Topology provides these. Remove topological protection and fields unwind, defects vanish, order evaporates. A universe with one extra dimension becomes topologically forgetful. Structure still forms, but it cannot stay. The universe is not built from particles, it is built from symmetries. Electromagnetism, the weak force, the strong force, all arise from gauge symmetry. Gauge fields live in space, respond to topology, depend on dimensionality. Change dimensions and symmetry behaves differently. In more than 3 spatial dimensions, gauge couplings acquire different mass dimensions. Many theories become non-renormalizable. Predictive power collapses. This is not aesthetic. It means infinite parameters are needed. Physical predictions lose meaning. 3 dimensions quietly sit at the edge. Enough room for rich symmetry, enough constraint for calculability. One more dimension pushes theories past that edge. The strong nuclear force works because color fields confine, flux tubes form, energy grows with separation. In higher dimensions, field lines spread too freely. Confinement weakens, free quarks may become unavoidable. Without confinement, protons fail. Nuclei dissolve again from a new direction. Dimensionality undermines matter, not just structurally, but fundamentally. Now we address something often overlooked. Why do we add spatial dimensions, but not temporal ones? Time has direction, enforces causality, breaks symmetry. Space does not. But this balance is delicate. In higher dimensional spacetimes, light cones reshape, causal domains fragment, determinism weakens. Initial conditions lose control over outcomes. The universe becomes less narratable. Stories require persistent causality, stable ordering, predictable evolution. Higher dimensions erode narrative itself. Conscious experience depends on ordered causation, memory retention, low noise. These depend on dimensional restraint, spatial limitation, controlled interaction pathways.
One extra dimension opens too many doors. Experience fragments. Once again, from an entirely different angle, topology, gauge symmetry, confinement, causality, experience. Three spatial dimensions appear not as a choice, but as a boundary condition for coherence. At this depth, something strange happens. The more carefully physicists study higher dimensions, the more reality seems to lose dimensions rather than gain them. This is not philosophy. This is one of the most rigorously studied ideas in modern theoretical physics. The holographic principle states, all the information inside a volume of space can be described by data on its boundary. This is not metaphorical. Black hole thermodynamics forces this conclusion. Black hole entropy scales with surface area, not volume. This suggests the universe stores information as if it were lower dimensional. Gravity behaves differently from other forces. It couples to energy itself, measures geometry directly, responds to dimensionality in a unique way. In higher dimensional theories, gravity often becomes dual to lower dimensional quantum theories, loses its independence as a bulk phenomenon. This leads to a disturbing idea. Perhaps extra dimensions are not where more physics lives, but where physics disappears. In ADS-CFT correspondence, a gravity theory in higher dimensions is exactly equivalent to a quantum field theory in fewer dimensions. Nothing is lost, nothing is added. Reality is re-expressed. This implies dimensions may not be fundamental. They may be representations, different descriptions of the same underlying structure. One extra dimension might exist, but not as an independent place.
Now we approach an idea that dissolves the question itself. What if dimensions are not ingredients of reality? What if they are consequences? In modern quantum gravity research, space-time geometry emerges from quantum entanglement, connectivity comes from correlations, distance is not fundamental. This means dimensions are bookkeeping devices, ways to organize relational data. If entanglement patterns change, geometry changes, dimensions effectively change, space becomes derived, not given. Adding a dimension does not add reality, it adds redundancy, a different encoding of the same information. What looks like one more dimension may simply be a different mathematical language, a reorganization of degrees of freedom. This is why extra dimensions appear in equations but resist physical manifestation. They are not wrong, they are non-literal. If space is emergent, then stable dimensionality reflects stable information patterns. Three-dimensional geometry may correspond to optimal entanglement scaling, maximal error tolerance, minimal redundancy. Not chosen, not imposed, selected by consistency. Gravity's unique relationship with dimension. Now we isolate gravity one final time, without resolving it. Electromagnetism lives happily in three dimensions. The strong force demands confinement, breaks in higher dimensions. Gravity adapts, spreads, weakens, encodes information differently. It is the only force that measures dimension directly, responds to topology, couples to everything. In many models, matter stays confined. Gravity escapes. This is not arbitrary. Gravity is geometry, does not recognize boundaries the same way, is sensitive to global structure. This suggests gravity may be the messenger of hidden dimensions rather than their inhabitant. If one extra dimension exists, gravity feels it. Matter does not. Information partially does. Reality becomes layered, not fully higher dimensional, not fully three-dimensional, something in between. At this depth, the original question is no longer stable. It has become, are dimensions physical spaces, or are they shadows cast by deeper structure? And physics has not answered this. One of the strangest tensions in modern science is this. Mathematics is perfectly comfortable with any number of dimensions. Physics is not. This mismatch is not accidental. In mathematics, spaces of any dimension are equally valid, Equations generalize cleanly, structures often simplify in higher dimensions. There is nothing mathematically special about 3. In fact, many proofs become easier, singularities soften, symmetry increases. From a purely mathematical perspective, 3 dimensions look arbitrary. Physics does not ask what is possible, it asks what is stable. Every physical structure must resist perturbation, survive noise, persist across time, encode information reliably. Higher dimensions provide freedom, but freedom is not always good. Freedom creates leakage. Every extra dimension adds decay channels, adds fluctuation modes, adds pathways for energy loss. Mathematically elegant, physically dangerous. This is why theories tolerate extra dimensions. Experiments do not reveal them. Reality seems to cap dimensional freedom. Without stating it explicitly, physics enforces a rule. Only dimensions that do not destabilize structure are allowed to be large. All others must compactify, freeze, disappear from experience. This is not anthropic, it is dynamical. Now we step into a territory that sounds philosophical but is rooted in operational physics. A dimension is not something you see, it is something you can move through, measure independently, encode information along. If no process can do this, the dimension exists mathematically, but not operationally. Physics cares about operations. In many systems, the effective number of dimensions changes with scale. Examples: electrons in graphene behave as 2D particles. Near black hole horizons, physics becomes effectively 2D. At very high energies, space-time may become lower dimensional. This suggests dimensionality is not absolute, it is scale-dependent. A universe might behave as 4D at microscopic scales, collapse to 3D at macroscopic scales. Or the reverse. Dimensionality becomes a function, not a constant. If so, asking whether the universe has one more dimension becomes ill-posed. It may sometimes. Observers interact at specific energy scales, use specific processes, access only certain degrees of freedom. They do not see all of reality. They see what remains stable at their scale. 3-dimensional space may be what survives observation, not what fundamentally exists. Now we introduce a final, unsettling idea, still without resolving it. Across physics, we see least action principles, energy minimization, entropy extremization, symmetry breaking towards simplicity. Nature does not use all possibilities, it uses just enough. Each dimension costs stability, predictability, control. More dimensions increase expressive power, but reduce coherence. A universe that wants long-lived structure, memory, causality, cannot afford too many dimensions.
3 dimensions may represent maximum complexity, minimum instability. Add fewer, too constrained, too simple. Add more, too unstable, too noisy. 3 sits between sterility and chaos. What if the universe had one more dimension? Becomes, how much freedom can reality tolerate before coherence fails? And physics does not answer this directly. It circles it. Dimensionality and conscious experience, a constraint few discuss. At this depth, it becomes impossible to avoid a delicate topic. Not consciousness as mysticism, but consciousness as a physical process. If thinking systems exist, they must obey physics, and physics is merciless about dimensionality. Regardless of interpretation, any conscious system must store information, update it reliably, maintain identity over time. This requires stable substrates, controlled interactions, predictable causal chains. Dimensionality determines all 3. Brains, biological or artificial, rely on local interactions, modular organization, and shielding from noise. In higher dimensions, coupling pathways multiply. Noise infiltrates faster. Isolation becomes harder. The system becomes more connected, less controllable. Complexity without insulation is not intelligence, it is chaos. Memory is not storage alone, it is resistance to forgetting. Higher dimensions increase entropy flow, open more decay channels, accelerate erasure. This suggests conscious observers are not just unlikely in higher dimensions, they are physically disfavored. Experience unfolds sequentially. It requires limited degrees of freedom, manageable branching, controlled feedback. Higher dimensions create excess branching, fragmented causality, loss of narrative coherence. Reality becomes untrackable from within. There is a recurring frustration among physicists. Mathematics insists on extra dimensions. Experiments remain silent. This tension is not accidental. Mathematics values symmetry, generality, elegance, completeness. It explores possibility space. Physics explores survivability space. These are not the same. In many theories, extra dimensions simplify equations, encode constraints, organize information. They may not be physical locations. They may be mathematical scaffolding, auxiliary variables, hidden structure, not extra space. The universe may not have more dimensions. Our descriptions might. Physics has made this mistake before. Epicycles, ether, absolute time. Extra dimensions may occupy a similar role, useful, predictive, non-literal. The danger is confusing representation with existence. Perhaps asking, does the universe have one more dimension, is like asking, does music live in frequency space or time? Both are valid. Neither is exclusive. Now we approach an idea that quietly appears in multiple theories. What if the universe does not merely tolerate three dimensions? What if it actively suppresses the rest? In some models, expanding dimensions drain energy from compact ones. Growth in one direction suppresses others. This creates dimensional competition, selective expansion, structural pruning. Three may have won a cosmic contest. Suppressed dimensions still influence constants, still affect vacuum structure, still leave subtle fingerprints, but they do not host dynamics, support structure, carry observers. They exist, but cannot dominate. Reality may not be passive. It may continuously resist dimensional expansion, damp unwanted modes, enforce coherence. Dimensionality becomes a regulated variable, not a fixed fact. At this level, the original question has transformed once more. Not, what if the universe had one more dimension, but what is the universe preventing from happening? And physics does not yet know how to answer that.
At extreme depth, physics begins to resemble information theory. This is not metaphorical, it is literal. We often imagine laws as rules that allow things to happen, but more accurately, laws prevent most things from happening. They prune possibility space, they stabilize outcomes. Without constraint, nothing persists, nothing repeats, nothing is knowable. Dimensionality is one of the strongest constraints of all. Each spatial dimension adds independent degrees of freedom, increases phase space, increases sensitivity to noise. In information terms, errors propagate faster, correction becomes harder, redundancy fails. A universe with too many dimensions cannot remember its own state. Three dimensions allow redundant encoding, structures can fail locally without global collapse, shielding, inside versus outside, surface versus volume, hierarchy, micro, meso, macro scales. This looks accidental, but it behaves like engineering, not design, optimization. Reality appears to continuously correct deviations, suppress runaway modes, restore coherence. Dimensionality is part of this control system. Not too few, not too many.
There is a reason this question refuses to go away. It strikes a nerve. We did not decide space has 3 dimensions, time has 1, laws are structured this way. These facts are imposed, not reasoned. Asking about an extra dimension questions the foundation of experience itself. As we saw, add 1 dimension, atoms destabilize. Add 1 dimension, orbits collapse. Add 1 dimension, information leaks. Existence balances on a knife's edge. This is unsettling. At shallow depth, the question is physics. At great depth, it becomes why coherence exists at all, why structure is allowed, why anything persists. Physics does not reject these questions. It simply has not finished answering them.
Now, carefully, we allow ourselves to speak plainly. The honest scientific answer, yes, but only if it is compact or suppressed or inaccessible or scale-dependent. A large, free, extended extra dimension? Almost certainly no. Not because it is forbidden, but because it destroys stability. Even if extra dimensions exist, we cannot move through them, we cannot localize objects within them, we cannot encode memory along with them. They are not places. They are parameters. Physics does not say 3 dimensions are special. It says 3 dimensions work. That is a very different statement. We end not with certainty, but with clarity. It does not use all dimensions, all symmetries, all possibilities. It uses just enough to exist stably. It is not an extension, it is a transformation. It rewrites forces, structures, information, experience. The universe we know would not survive it. The real lesson is not about dimensions. It is this: reality is constrained because constraint is what makes reality possible. Freedom destroys, structure survives. Perhaps the most remarkable thing is not that the universe lacks extra dimensions, but that it has exactly enough to allow matter, memory, meaning, minds that can ask this question. And that balance may be the deepest law of all.